Hello and welcome back. In this video, what we're going to be doing is talking about virtual methods. You can kind of think of this video as being inheritance, part 2, the super cool stuff. That's right. By the time we get done with this video, you're going to know how to do some really neat things with virtual methods through the use of inheritance. Now, in the last video, we saw that through inheritance, we were able to create hierarchies of classes. Now, what do these hierarchies of classes do for us? Well, they helped us to eliminate redundant code while also providing better organization in our program. And that's, well, very important, very good stuff. But there's a third feature that we gained from using inheritance that was not discussed. This feature is polymorphism. Now, we've talked about polymorphism very briefly in the past when we had the introduction to object-oriented programming. We simply gave you a very quick definition and we moved on. We were waiting for the real lesson of polymorphism to come, and, well, here we are. Now, we decided not to talk about polymorphism in the last video, even though it is heavily tied to inheritance, for the simple fact that we were trying to stay focused on the basic concept of inheritance. Now, in this video, we'll be exploring polymorphism through the creation of virtual methods. So by the end, you should have a very good understanding of what polymorphism is. Now, we have 5 objectives to cover in this video. Let's go ahead and take a second and jot them down so that we can mark them off the whiteboard as we go through them. First and foremost, of course, is going to be what is polymorphism. Okay, once we've taken a look at what polymorphism is, that is going to bring us into the world of virtual and override methods. So at that point, we need to take a look at them. So virtual and override methods. In fact, I'm going to throw some question marks in here because we're asking ourselves, what are they? From there, syntax. Now, if you've been following very closely through Volume 2 of the XNA Xtreme class, you'll know that virtual and override are just modifiers. So the syntax, well, you've already seen the syntax in the past. It's just the syntax of creating a method, or be it a property, or whatever it is that you're going to be, well, overriding or setting as virtual. But in this case, I'm just going to write down syntax and just keep in mind that you already know it. We're just going to be showing you how to go about creating virtual and override methods. Now from there, we're going to look at something that's very important to understand and very cool, because it is really going to just rip the lid off of power, I guess you could say. The things we'll be able to do is just amazing with this. And that is the nature of virtual methods in hierarchies. Okay, so let's go and write all of that down. So the nature of, and we'll just keep things short, VM, virtual methods in hierarchies. There we go. Okay, and basically what I'm talking about is we're all comfortable with calling on methods. We have method execution. And we saw in the last video when we called upon a method to execute when we had cast a type to another type, well, the type we had cast it to's method was called. But we weren't dealing with virtual methods. So now dealing with virtual methods, everything changes. So the nature of virtual methods within a hierarchy is very interesting and offers a tremendous amount of power and flexibility. So we'll be taking a look at that. And then finally, of course, rules. That's right. So let's go ahead and just jot rules down. So rules of both virtual and override methods. Excellent. So for getting started, let's go ahead and just jot a line down here. All right, for getting started, the very first thing I want to do is cover what is polymorphism. Now, before we start looking at any code or getting technical with descriptions or anything, let's just take the word itself and break it down. So we've got polymorphism. So we could break this down into poly, meaning many, and morphism. Let's just take a look at morph, which means form or shape. So we could say polymorphism is many forms.
Or you could say being of many forms.
Exactly. And believe it or not, they saw this in the last video. At the very end, there was a little bit of polymorphism going on. We didn't even mention it. We were so slick, just cruised right on through it. Now, if you caught it, excellent. And if you didn't, try pausing the video right now and thinking back to the last video, where did you see a form of polymorphism? All right? Now, if you did pause it, hopefully you've unpaused it by now, let's take a look at a line of code. Now, we're going to stipulate that the game item class exists. We're going to stipulate that an enemy class exists. And the enemy class is an extension of game item, or derives from game item. Now, let's also stipulate up in main that we have instantiated the enemy class into a spider variable. Okay? So, with this line of code, game item item, so I am creating a new variable, equals, instead of saying new game item, how about this, spider, because we know spider is holding a reference to an instance of spider. So spider, and then use that new operator that we learned in the last video, as, so spider as a game item. Ooh, very, very interesting. Take a look at this. So what does item hold? Now, we talked about this in the last video. Item is a game item, but it is holding a reference to a spider. Now, let's make this even more interesting. A spider is a game item. This is why we're able to just easily do this, okay? So, couldn't you say now that we could just pass the spider off as a game item? I mean, in essence, it's a different form if you want to look at it that way.
Right, it's a different form, but it's also the fact that the spider is, you could say, polymorphic at that point, because there's multiple forms in place. A spider is an enemy, obviously, but it is also a game item because enemy derived from game items.
Ooh, so what if we made it more interesting and did this? Just for you, Logan.
All right, what you got?
Game item. Derived from that, we have pawn.
Oh yeah, going back to the first example.
Yeah, I know where you're going, so I'll give you some room to work here. And an enemy.
So yes, and then there's even more forms of enemy.
From this, we have created a spider.
So a spider, what is a spider? Well, obviously it's an enemy, because we made it from the enemy class.
Check.
But it's also a pawn, because enemies inherit from pawn.
That's right.
And it's also a game item, because pawns inherit from game item. So there's many different forms in which we could store a spider. We have options of enemy, pawn, and game item, and all of those could easily hold a spider object.
Exactly. Now, if we were dealing with something that was, well, took in game items, we could, well, let me not get ahead of myself, and as I'm going to show that again in just a second. However, we could just start out with a game item and create a new enemy straight into it. We showed that in the last video, but we kind of just said, oh yeah, and you can do that, because we were waiting for this video to put emphasis on it.
It's really the same idea, though. It's not so much when we had stored, like even in this example where we say we're storing the spider in that item, we're not storing a reference to the variable spider, we're storing a reference to the same thing that spider references, to the object.
That's right, to the instance.
So after that, yeah, exactly, to the instance. So after this, item holds a reference to the object spider, and the spider variable holds a reference to the object spider.
That's right. So
it's not like item points at spider or anything. It's that both of them point at the actual spider object.
That's right. What you could say, the actual spider object is this.
Right, because
and this backs up what Logan was just saying. It is an enemy. It is a pawn, and it is a game item. But by doing this right here, let's all think back to the last video. What did we just do? We just adjusted our scope on what we can see through item, where we've made it such that we can no longer see any new members that were defined in pawn or enemy, because we've cast it all the way back up to a game item.
Right, because in that way it was stored in the form of an item.
That's right. Now, let me go ahead and make this a little bit more interesting, because the following pieces of code, this is the kind of stuff we're going to start doing a lot. What if we had something like this? Game item equals new enemy. Get used to seeing stuff like this. What have we done? We have created, so here's our heap. And squeezed right over here is our stack. We have just created, so here's the stack with stuff already on it, item. And we have an instantiation of enemy. Alright, so here's our instantiation of enemy on the heap that contains enemy, pawn, using the example drawn above, and game item. Now, we point, the reference is to the object. But now I'm going to start using dash lines to handle type pointing. But our scope is of game item type. Does that make sense, Logan?
Right. That means that if we use item just to pass the reference around, we're referring to the entire instance.
That's right.
But item is of type game item, which it should know about because of the fact that the type object is also loaded.
That's right.
So it's going to treat item like a game item, nothing more.
Exactly.
Even though it can in fact hold a reference to something that can be more than a game item.
And even though right here we know it's an enemy, it's in black and white right in front of us. But the moment you start passing this guy off to other classes and all, they don't know. They don't know it's an enemy. Not without doing some special checks. And this is what we talked about in the very end of the last video, where we said exercise caution when dealing with these, when casting in a lower level direction towards the final derived class, because you can get in trouble. Because again, when we start getting into other classes, we don't know what the game item is. It just, a game item, or was it an instantiation of a pawn, or was it an instantiation of an enemy? Because it could have been all of those, and all of those objects would truly look different. Okay? Anything you want to add to that?
Right, but the key is if you're casting in the other way, if you're casting towards base,
yep.
It's nice that is a very safe operation, that as it's casted to base and you pass it off to some other method or someone else has to handle it, they don't really necessarily have to know that it's an enemy.
Nope.
If they're going to do game item type things to the reference item,
then they're good.
That's one of the key things about polymorphism, is that one can safely affect an instance as a game item without affecting anything else or without corrupting any other aspect of that game item.
Precisely. Let me go ahead and jot one more example down that they're going to see often. So this one, or how about this? We're all familiar with lists now. So what if we had a list holding, or of type game item, or we could say a list holding game items, called game items. And then we took this, and let's go ahead and create the list. So equals a new list of game items. And then we turned around and said game item dot add, and send in a new enemy. What we've got going on here?
It's really the same thing, just more of them.
Same thing, except for now what we're doing is we're instantiating an enemy and we're storing that reference in a list. Okay, but what does the list hold? The list holds a list of game items, so it doesn't have to be only enemies that get put in there. We could have enemies, we could have players, we could have props, we could have anything that basically derives from game item. Or we could have just game item itself, but in the way we've preached it, it's more or less a generalization or an abstract idea. Okay, so in all of these particular cases right here, you have been witnessing the use of one form of polymorphism and the simple fact that we're treating a class as different types within its hierarchy. Okay? Now, with that being said, we can make things even more interesting. We can now start to get into a world of change, because at this point, the way we've been handling the taking on different forms or different shapes is by just, I guess you could say, by we're treating it as a different type within the hierarchy and controlling its scope of what can and cannot be seen. Is that fair to say?
Yeah, that's pretty much exactly what we've been doing.
But now we haven't been actually changing anything. When you hear that word morph, you want to see something truly change from one form to another. We are seeing that here, but I want to see it change. And through the keyword virtual, we can cause behavior to change in derived classes. And this ability, of course, offers a great deal of power and flexibility. And I put together a very quick real-world example. Let me read this off to you. So, all applications, they can print, right?
Right.
Just about all applications. I mean, here we are inside of Photoshop. It can print. Word can print. WordPerfect can print. And my browsers can print. Most applications that you're going to do any kind of
pretty
work
much
on can
any
print.
application that deals with documents.
Yeah, that deals with documents. I like that. Can print, okay? Now, of course, if we can print, what are you going to print to? A printer. Now, in the world, there are many types of printers. They come in many different flavors. We've got inkjets. We've got lasers, thermal, bubble jets, the dot matrix, and the list goes on and on, right? Now, when you hit the print button, what are you expecting to happen? You're expecting your printer to come to life and print out a piece of paper with the data that you sent to it. The way that the printer prints the data, who cares? It's of no concern to you. As long as you hit print and your document prints out on a piece of paper, yay, you've accomplished exactly what you were looking to do. Print out the information, okay? So, and that's the key thing here, is how the printer prints it is of no concern to you. So, we could say that there's a contract between the printer and your application, such that the printer is guaranteed that it will have print functionality available. And that really is very important here, because in the applications that we're going to be getting into real soon, we are going to have classes that we're going to create, classes that will be derived from other classes, where we will have to guarantee certain behavior will exist. A very simple example is just our game items that extend into pawns, which extend into players and enemies, and having props also be an extension of game item. Update. When you start dealing with a game, it's very important to have game items have update. So we need some sort of contract between, you could say, our engine and these items, that they're going to have an update so that we can loop through all of our items and call upon their update and let them take care of themselves.
The idea is that through the idea of a printer, you've put forth the requirement to have print functionality. What this means is that as long as an application knows about this printer idea, it can print on any printer without knowing the printer specifics.
That's right.
Because it knows about the contract and it knows that every printer has print functionality, from that alone, it can print on a laser printer the same as it would print on an inkjet printer. And the application itself wouldn't have to be rewritten for any of these different types of printers.
Oh boy, that'd be loads of fun. Let's draw some pictures. Pictures are always fun to draw. Okay, so we have, no laughing, Logan. We have a factory. Because we know printers come from factories, right? Okay, yeah, Logan's smiling, no smiling. All right, and this company, Company X, they create thermal, they create inkjets. I'm going to back up the idea that you just said. I'm just going to put in a graphical representation is what I'm going to do. And they make lasers. Sweet. So this factory is pumping out all of these different guys. And now, of course, all printers need to be able to print. So they're all going to have print functionality. So I'm just going to call it PRNT just because I don't have room. Now, elsewhere, we have an application. And this application has the ability to print your document. What printer are we printing to? Everybody could have a different one that's using the same application. So in this particular case, could be a thermal, could be an inkjet, it could be a laser. From our point of view, the functionality is going to be the same. I'm going to hit print, and I'm going to get a piece of paper that's printed out with my document on it. But what actually happens inside of here is going to be different in each of the printers. So we could say that these printers are polymorphic because each of them will handle their own printing in their own way.
Right. The base idea of a printer might not even have any specification for the mechanics of putting ink on paper or putting toner on paper or use of a thermal system.
That's right.
All it says is that we can print, maybe would say something in case, if there's something common, like let's say all of these printers work with paper. It might say that we have some paper loading ability, but we'll leave it at that. Then the specifics are let up for any actual printer that follows and implements the print contract.
Right. Now, and the same thing applies here. Check it out. Watch this. If we have Johnny, our happy programmer, and he's writing classes that's going to be used by a game engine, we could have an enemy, we could have a player, we could have a prop, and they all have to have, I'm just going to call it U, but it's update. They all have to have an update. So he's going to write all these classes, and then we're going to turn around and hand it to someone else who is creating the game engine. And the game engine, in the loop, it's going to run through all of our items, and it's going to call update. Check it out, same thing.
And that means any class that Johnny writes could be dropped into the engine, and the engine will be able to update that and have any appropriate action take place, even though the engine itself wasn't aware of that action when the engine was created.
Exactly, and that is very powerful. Let's say that we have this printer company that suddenly designs a brand new, crazy, high-tech, holographic style printer. I believe it was you, Logan, the other day that mentioned hologram printers would be quite cool. So they print one, or they create one. Go ahead, what were you going to say?
But the cool thing with that is if you plug that into your application, you don't have to change the application. You just get documents that are written out as holograms.
You got it. So it understands when the application sends print and it sends its data, it knows that now it's going to have, you know, this little swirly document that's going to be swirling inside. There's my swirly graphics. So that's what's going on. But again, as Logan said a second ago, that's where we get into a great amount of flexibility because we can extend our application later in time by adding new game items or adding new printers if this was, you know, a real-world type scenario. And nothing breaks. It would be awful if a new holographic printer was designed by Canon and then all of a sudden every word processor on the market had to be rewritten to support it.
Or even worse, it seems like printers always have a new model almost every year now. Or
how about every week?
So if you had to redesign the application just because a new version of the same printer came out.
Right.
That's another application. That way new classes can be written, not entirely new technologies, but just a new version of a printer comes out, yet it works the same with the application. No application changes are necessary to support it.
Exactly. So this is all fine and dandy now, but what does this have to do with inheritance and polymorphism? Well, this brings us up to virtual and having virtual methods. Let's go ahead and jot that down. So first of all, what exactly is a virtual method? A virtual method is a method that can have its implementation changed or overridden in a deriving class. The base implementation is still there if you need it. All you need to do is simply explicitly call it through the base keyword. And we've seen how to do that in past videos, okay? But imagine if, with all of these printers, they all had a base printer that they derived from. Okay, so let's do this. And this. And this. And we'll clean it up a little bit. Oops, well, what do you know? Eraser doesn't work today, so we won't clean it up. That's okay. So right here, this is just a base printer, and it's going to contain print. Now let's think about printers for a second. They all have something in common. When you print a document to a printer, what does it do? If it needs to come out of standby, it comes out of standby, and then it loads a piece of paper, and then the printing begins. They all load a piece of paper. Okay? So, since this functionality is common throughout everybody that is going to be derived from this base representation, then we could start out by having a virtual method exist in here called print, And with it, or within it, what we can do is go ahead and say, if necessary, let's go ahead and warm up the printer. All right, very good. Let's go ahead and pull a piece of paper in. All right, very good. And that's all. Now, with all of these other printers, they can override that virtual method. But check it out. Here's the neat thing. In overriding it, we can have a completely new, what's the word I'm looking for? Suddenly just lost it. Implementation. We can have a completely new implementation, or we can call upon the basis implementation and then add to it. Or we can add to it first and then call on the basis implementation. Can't believe I just forgot the word implementation. It literally just slipped outside of my head. Okay, so in this particular case, wouldn't these printers want to first say, let's call upon the basis implementation to work? That means if necessary, printer loads up, loads a piece of paper in, and then inside the particular printer, it would handle the mechanics that it needed to in order to actually print the data out to that piece of paper that's been loaded. Okay? And that would be different in every single one of these classes, if these printers were actually classes. And this exact same functionality applies for us over here with old Johnny. Johnny, instead of just writing the classes, Johnny, let's say, starts out with game item. And Johnny goes, every single game item has to have update. Why does it have to have update? Because we've established a contract between all game items in the engine that an update will be available. That's the key thing here. Well, since we've done that, we could go ahead and create a virtual update method. And then all of the classes that derive from this can then, if they want to, they can just completely ignore it and they just inherit it, and they now have the basis virtual implementation of that method, and that's what would get called. Or they could override it, so that's the other key word that's starting to show up more and more here. Or they can override the basis implementation with a new implementation that is specific to the class at hand. So let's say that enemies in their update, they need to seek out players. So we're going to call other methods that handle calculating where the player's at, yada, 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 AI type stuff. A player doesn't need that. He's getting input from you, the player. You're controlling him running around the screen. So in our update code, there would be no reason inside here for us to go out and, have the computer calculate where the enemy is for us, and using the same code basically that the enemy has. We don't need AI. We bring I to the table, actual intelligence to the table. We don't need artificial intelligence. And the prop, man, that tree better stay put. I sure don't need the tree sifting through some sort of AI routine trying to track down where a player's at or an enemy's at. So he doesn't need it whatsoever. So since we now have the ability to not only extend the class, we can now go in and extend its behavior or completely change its behavior. So with game item, we know that everybody needs to move. You might be thinking, well, why does my prop need to move? Let's pretend that we could have a rock slide, or that your character could walk up to a crate and push the crate along. The crate's just a prop, right? But its position is moving in the world. So inside game item, inside update, we could have something like move. I'm just throwing real quick words in there. Later on, we could think about exactly what we want to call the word. So move, right? But then, enemy, player, and prop, they could all just simply inherit move. So they could call upon their basis implementation, which would run move, and then we could add to it. Enemy, call upon AI routines to find player. Player, call upon your polling routines to find out what type of input has come from the real world player. And prop, sit there and look pretty. Okay, so we can basically go about extending the functionality or changing the functionality altogether if we want to of the base virtual behavior. Logan, is there anything you want to add to that?
Another key thing to point out is just remember that with virtual, it's like you have the option of extending a method's functionality or completely overriding it. As a matter of fact, the moment you override it, it's actually the other way around. It's up to you to include or not include by accessing the old functionality using base.
That's right.
What's cool is if you go back to the printer example and think about how the thermal, the inkjet, and the laser printer were all getting the functionality of load paper. through the print function. Basically, load paper was defined all the way back up in the base printer. And they were all using that and then extending it. So they were accessing some base functionality and then adding some of their own.
Right.
What about the hologram printer? What if it doesn't print on sheets of paper? It has the option of, when overriding the print functionality, to disregard any form of paper loading and instead print to a plate of metal or a plate of plastic or a plate of foil.
Because it never needs to warm up and it never needs to grab paper because it doesn't work with paper.
Right.
So it could choose not to call upon the base's implementation.
Exactly.
That's very nice. Matter of fact, Logan, let's go ahead and code that for a few minutes. I'll do it on the whiteboard to point stuff out. Now that we are kind of comfortable as to what virtual and override is, let's show it and just kind of wrap this package up all nice and neat. So I'll go ahead and come over here and add a new whiteboard to the scene. And let's do a little coding. So let me start out with a class. Give myself plenty of room. Actually, you know what? Let me give myself a lot of room by scrolling up so it doesn't jump. There we go. So I'm going to start out with a class called printer. So that R in there. And printer, let's say that it has a print method that can be overridden by anybody that derives from printer. Because printer, the goal in our little design here, printer is not the end result. It's a means to an end, but it's not the final printer. So this is kind of our base foundation. This is the generalized idea. So we're just going to give it one method. Check this out. It is going to be public. It's going to be virtual. It doesn't return anything, so void. And the method's called print. And it's going to take in some data. We have to have that in there because signatures have to match. Now, Logan, I'll have you code this in a minute just to demonstrate to everybody, so I'll just make this real brief with a simple write-out. Warm up, so warm up if necessary. And then let's tell it to load a piece of paper. So load paper. And that's all we've got. So the printer class is, you know, it does something, but of course that's if we're pretending the warm up and the load paper really happened. It does something, but it's still kind of abstract, right? It's nothing specific other than just pulling a piece of paper in.
Right, and it wouldn't be very usable on its own.
No, it would not. So now from here, let's do this. Let's create another class called laser printer. That is derived from printer. Now, of course, this laser printer needs the ability to print. So, and of course, we have just inherited print. It's public, right? But it's virtual, so we have the ability to write our own implementation. So let's go ahead and come in here and do a public override void print. Once again, all signatures must match to do this, so it's going to be a string that's going to come in, the parameter, called data. All right, what are we going to do inside here? Well, for my laser printer, I need it to warm up if necessary, and I need it to load paper. So check this out. I have to have the base class's implementation of print execute. And I have to have it execute first, so I'm going to say base dot print. This will have the print method in printer execute.
Though we'd probably have to feed it data in order for it to work, because the base
we absolutely
functionality
do.
Does take in the string data.
I am interested in why I have managed this. This just happens from time to time, and that's just the fun of dealing with, there we go, Photoshop. But my eraser, let's see if it actually changed back. Nope, my eraser is just gone for today. Okay, so let's go and pass data to it. Good catch. And then we'll do some more writing out stuff. So now that we have warmed up the printer, we've loaded a piece of paper, now we can do whatever's required for laser print. Dot, dot, dot. And we can print out our data. Excellent. Now let's come in here and create another class called inkjet printer. And inkjet printer extends printer. And of course it needs to be able to print. So we'll same thing. Public override void print string data. And then same thing in here. Let's first call base.print and of course send it the data. And then we would do whatever was required for inkjets to print. And of course we'd print out the data. And close that off. And close off the other one right here. Yeah, that's closing off. Just trust me. Okay, so there we go. Now we have created a hierarchy, a very simple one. You could say we have one parent, two children. The hierarchy is going to look like such. So we've got printer. And then through inheritance, we've extended into a laser printer. I'm not going to write all that out. And an inkjet printer. And following with UML, specifications, laser, and inkjet derived from printer. There you go. So this is what we have created. Now, we have got print methods that have now been overridden. So this means when we were to, let's do something like the following. Just at this point, this will represent us being back up in main or in some other class. So now all I have to do is come in here and say inkjet printer. And then I need to give my variable a name, so my printer equals, and then just create a new inkjet printer. And now I can turn around and print. So I can say my printer dot print, and of course I better send it a document, so we can say test page. And there you go. Just change my color real quick. Let's see what happens. So this guy right here, of course, is going to create my instance of an inkjet printer. And then when I call upon its print behavior, well, let's come down here to its print behavior. Okay. So the first thing that's going to happen is we're going to call basis print, and we're going to send it data. So we jump all the way up here, and we're going to say warm up if necessary. Then we're going to say load paper. Then, of course, at this point, we're now finished So we continue with execution. So the next thing that's going to happen is going to be the inkjet print. This is whatever voodoo happens inside a printer to engage print heads and all that good stuff. And then our data, which is going to be test page. There you go. Very simple. I mean, guys, it really is this simple. There's no reason for us to turn this into a 4-hour video covering virtual and override methods. The key thing is use virtual if you have a method that needs to have its implementation changed by a deriving class. It's that simple. And then in the deriving class, use override to indicate that that is going to be a new implementation that you're adding in there. Okay? Logan, let's go ahead and pull up Visual Studio real quick and create this just so that they can see that the exact same results do exist. So let's do a new console app.
All right, here we go with a new console app. And waiting for it to load, so I take it we'll need...
Okay, so we're going to need a class printer.
So we'll make a class printer. And class printer is going to have a public virtual void print method, which takes in the string called data. And
let's go and do a couple console write lines.
Right, we need to say that we're warming up and possibly loading paper.
Yeah, warm up if necessary.
So let's do...
you were going to do it like me.
I was going to try to just type out your shorthand. That would have worked really well.
Sweet. So console.writeLine, warm up if necessary.
So, warm up if necessary. Alright. And also we need to...
load a piece of paper.
Load a piece of paper. So load a... Alright.
Okay. Now let's go ahead and extend our printer class into a laser printer.
Okay. So let's make a class for laser printer. It extends printer. And inside of laser printer.
Hey, there we go.
Alright. So we want to extend the print functionality. We'll do this with public override.
3 R's. Awesome.
And this is going to be...
So it's going to be a void
print. And IntelliSense has that as one of the valid things. The cool thing with selecting a virtual method out of IntelliSense
is that it automatically throws it all down with a call to base.
Right. As soon as you let it drop it in, it drops in print, it drops in the parameters, and it also drops in a call to base.
That's very, very nice. And actually, we do want to do the base first because we do... See, we could do the base first, we could do it at the end, we could do it in the middle of our new implementation.
Right. Because you call it inside of the method, it's up to you to call it at any point inside of that method.
It's just like a regular method call. I mean...
Yeah, it really is.
That's all it is. But obviously, in this particular case...
I was about to drop it at the bottom, which meant we would have tried to print before loading paper.
Yeah, which would have been bad. Hey, I've had printers go defective and do that. It's not fun. Okay, so now that you've got it warming up and loading a piece of paper, let's go ahead and tell it to just say laser print ... All
right. Laser print. So we can tell that we're now inside of a laser printer doing something. And then the final thing we do is actually output...
in this one, though, actually do a quotes /n first. Let's just do a new line to push off of up there.
Okay, just to separate...
Or add a new line there.
I mean, to separate the data from the fact that we're in a laser printer.
Or that. There's 500 ways to do it.
Sure. All right. Then our final write line will be to write out the actual data for printing.
So it's just data.
All right.
All right, very nice. Now, if you want to copy that whole thing and paste it so that we can just simply change it from a laser printer over into an inkjet printer.
So copy and paste it below laser printer. This final printer is an inkjet printer, so inkjet printer extends printer. It's going to override the print method. And inside of inkjet printer, we'll just change this to indicate that this is indeed an inkjet print.
All right, very good. So let's go ahead and jump up to the top now in main and make use of these new classes. So let's go ahead and create an inkjet printer.
Alright, so I'll make a new inkjet printer. We can call it my printer. And we can set it to be equal to a new inkjet printer. Then we can turn right around and use our new my printer to print out the data test page. Just made some stars around it. Again, to just to separate it from the other stuff.
Yeah, it's our data.
So this will be a test page. And yeah, there we go.
There we go. Okay, and let's do a console.readline just to halt execution.
Console and read line.
All right. So in this particular case, what Logan is doing is after instantiating an inkjet printer, he's making a call to print. So with our inkjet printer, the way it works down here, when he calls print, this is an overridden or an override method that has overridden the base. So in here, that means think of the base implementation as, well, it's not going to happen now. It's up to us to put what we want to occur in here, our own implementation.
Which makes sense with the word override, and that makes sense that you're overriding the old one and specifying some new functionality.
Exactly. So what's he going to do first? Well, we're going to gain access to the old functionality by making an explicit call back to the basis print. So the base print, we jump back up to who we inherited from. That's our base. So here we go. So we're going to print out, warm up if necessary, load a piece of paper, and then we continue. Inkjet print. Another just empty line, and then we print out test page, and we're done. So let's go ahead and execute this Logan and make sure that it gives us what it should. And there we go. Warm up if necessary. Load a piece of paper, inkjet print, and then here comes our actual document, test page. Very nice. Now watch how easy this is to change. Go ahead and hit enter for me, Logan, and change it from an inkjet printer to a laser printer.
Sure. We could say that my printer is a laser printer. So we'll store a new laser printer in my printer.
And all he's got to do is run it. And look at this. Once again, we still warm up if necessary, load a piece of paper, do all the stuff for a laser printer, and print out the document. Now go ahead and close that and add me a new printer. Give me your hologram printer.
Ooh, okay. Let's jump down below inkjet printer. Let's make a new printer. A class holographic printer. And holographic printer extends printer. Inside of holographic printer, we want to override the print method, so public override void print. And if I didn't use IntelliSense, obviously it's still up to me to make sure we take in the same parameter. Now, in this holographic printer, we do want to have print functionality because we need to maintain that contract for being a printer. But since it's a holographic printer, we're going to say that it doesn't use paper at all. So it has no need for any form of loading a piece of paper. Maybe it doesn't even need a warm-up functionality because it has no ink it needs to deal with.
Okay.
It purely has a laser that writes directly on the medium.
Okay.
So inside of print, that means we don't need any of the base functionality. We're going to purely override it. So I'll ignore base.print.
And just write out something cool sounding for, fire up hologram engine.
Yeah, let me start stealing some console write lines. So we could say calibrating laser engine. And then do a new line and then a print. So we can steal some of this stuff. So something entirely different from any of the other printers. And then the new line and then print.
Okay.
As a matter of fact, just to keep with the format, let me actually do this. We'll say hologram or holographic print. So holographic print, calibrating laser engine, and then we do our actual printing.
All right, very nice. So let us go up to the top and just, at this point, this is how cool this is. We just change out our printer.
So we change the laser printer over to a holographic printer. There's holographic printer. We run holographic print, calibrating laser engine, print.
So notice we didn't warm up. We didn't grab a piece of paper because that was irrelevant for this new high-tech type of printer. And if he changes it back, so go ahead and change it back real quick. Just make it a inkjet or laser, doesn't matter.
So let's make this back to a laser printer.
And he runs it, and now it warms up, loads a piece of paper, fires out the test page. Very, very handy being able to override methods that were implemented in base classes.
So now functionality can be tailored for use for any specific class. And you're still allowed to reuse code in the, I guess you could say, in an inheritance manner, because in a derived class, you can specify functionality that makes sense for the printer at hand in each of these cases. You can then reuse functionality if you need to do the same thing. So for anything that is the same, reuse the functionality instead of rewriting duplicate code.
Right.
But in a case that differs significantly, you have the option of completely overriding, but still maintaining the contract put forth by a printer, and in that way still being able to use the exact same print functionality regardless of what printer it is and how different its print functionality may be.
That's right. Now, just to show them that we can call base's implementation anytime we want, let's break one of our printers. You're calling the laser printer at the moment. Let's go ahead and take his base.print call and move it down to the bottom after the data.
Like that.
So now we've broke the laser printer if we run it. So laser print, and we're just spitting out stuff, but we haven't warmed up.
We printed out a test page, and then we warmed up, and then loaded a piece of paper.
Yeah, this is bad, okay? So the idea was just to demonstrate that you can call the base's implementation at any point. You get to pick when, or you can avoid it altogether. Just in this particular case, comment it out and run it one more time because you're right there at it. And run it. And now look at that, laser print, it prints out a page, but we never warmed up and we didn't pull a piece of paper in, so we definitely need to take our printer into the shop. It's got a problem. So it is that simple. Virtual and override. I have seen beginners get really confused by the concept of, oh, I'm changing stuff, I'm confused. Don't be confused. It is as straightforward as we have demonstrated here. It really is that simple. All right. But now, let's go ahead and do this. I'm going to change my color back real quick. And I'm going to jump back over to our first page. Now, we've taken a look at what polymorphism is. So at this point with polymorphism, we've seen how we've had types represent different classes, or class represent different types. We have seen how we can have a method take on different forms in different classes that are derived from its original implementation, its base class. So we've seen two different forms of polymorphism. We've also taken a look at how to set up virtual and override methods. We've seen what they are, and we've seen how to actually implement them through syntax and all. Now we're to what I think is probably one of the most important things to understand when working with overridden methods, okay, and casting. This is really important stuff. The nature of virtual method execution in a hierarchy. Let's go ahead and bring up a new sheet of paper real quick. And there we go. Hide this. And I've got just a very simple demonstration I want to write up here so we can trace this through, because this is where the stuff really starts to get interesting. Look, and we'll have a thing where we've got class A, and what class A is going to have is going to be a public, virtual, void method called show. And inside of here, all we're going to do is write out, in this particular case we're in class A, so we'll do A ... point show. Just to represent, we're calling A's show. Okay?
It's very simple, show, and basically just to prove that this is the method that goes with class A.
That's right. All right, then we're going to do a class B. And we'll say class B extends class A, and is going to have a public override void show, and same concept here. We're just going to write out that we're in B's implementation of show. Then we're going to take it one step further. We're going to create class C, And class C is going to extend class B. So now we're making our hierarchy one deeper. It's like going game item, pawn, enemy. And inside here we'll have a public override void show. And we'll write out that we're basically executing C's show. And close it and close it. There we go. So we have got 3 different classes. If we were to draw out a representation of this down here, what we've got is A, we've got B, which is derived from A, and then we've got C. Everybody has their own implementation of the show method through the use of virtual and override. Now, what we are interested in here is what happens when we start using casts, when we start focusing on a different type, okay, within this instance. So if I instance the whole thing, we know the instance would look like this. So the object itself would be the whole thing, okay? But the question is, with our current variable, what type are we looking at inside? What type are we acting like at the moment? Okay, so let's to show you what I'm talking about. Let's say I wanted to create an A class. We'll store the reference to it in A. But it needs to be a new C.
Which is perfectly valid because, in essence, C is also an A.
That's
it's
right.
also a B.
C is a B and an A. So then if I was to turn around and say A.show, what happens? Let's just draw a little line right here. Well, before answering that, I want you to think back to the last video. We demonstrated doing casting just like this in the last video, and then when we called upon the method, I believe we were using the method update in that video, what happened? We saw the type that we were currently set as, we saw that particular method execute. Meaning that back in that example, where we had game item and enemy, if I called on enemies update, it ran enemies update. But the moment I said create a game item and store an enemy in it, and then I called on that items update, that update ran. The reason was that the 2 updates, each of the updates, they were completely independent of one another. Virtual and override were not involved, okay? Meaning that down here in enemy, we had hidden the override method that was inherited from game item. He had been hidden. So enemy had his own fresh implementation. And how did we pull this off? By using the keyword new. So we just said, public new or new public, doesn't matter which way you use the modifiers, but new public void update. Okay? Now, because of that, when you cast to a particular type, that type's method will get fired because it is the most derived method. Now that may sound very confusing, but it's going to make a lot more sense in just a second. With the current example that we have now introduced virtual and override. So in virtual and override, who contains the most derived method? What do I mean by that? Well, even though we're pointing at A, actually let me draw the heap out. I'm going to draw basically the same thing, but this is going to work a little bit better for me here. So here's the heap. And on the heap, I've got an object, an instantiation of the class C. So C. What inside of C do we have? We've got C. We've got B. And we've got A. Now, right now I'm not going to draw the object types out and all that good stuff, But what I want, well, actually I am. And here's why. So this is going to be A. You know what my divider line's for, don't you, Logan?
For the method lookups?
You got it. Man, I don't have erase. Ah! That's why that's open. And then here we got B. And then down here we've got C. So our object types that are sitting there. And C knows that he's linked up with B and A. All right. But now we have a virtual method in there called show. Now this is our method lookup table. And then it is overridden in B, and it is overridden again in C. Now we've got the stack. And the stack's cruising right along with all sorts of stuff in there, and suddenly we put the variable A in here. Now, what type is variable A? Its real type is a C. That's the object type. That's the instance, okay? The object is a C. But who does he point to? This is very important. He points to, once again, I'm going to do this, so there's no confusion. The reference is to the object, period. Now, what type are we pointing to? So I'm going to use my dashed lines for that. Just like in the last video we saw, the type that we're pointing to is A. Why? Because look over here. A is the type of A. Okay, that's the type we defined it as. All right, so far all is good, and it matches up with what we said in the last video, but here's where it comes in. We say in this line right here, which doesn't have a terminator, there, now it's valid. We say in this line, call show from A. So show from A, we're going to look at its lookup table, its method lookup table, and we find show. Oop, but show is virtual. This means that it could be more derived. Okay, it could have a further implementation towards C.
That's the purpose of virtual.
That's right. So since it might, we need to look up the next guy in the chain and see if this is the most derived version of it. It's overridden. Good. So there is a new implementation, so we're excellent. But wait a minute. There may be yet another one. So we have to go to the next guy. And what do you know? He also contains a show method that has been overridden. All right, so who contains the most derived method, if you will, of show? C does. So when I call upon a.show, since A, the object is a C, okay? Since that's the case, and C contains the most derived version of the show method, what's going to be shot out to our console is going to be this. C, show. Even though, based off of the last video, it would look like, or you would think that, well, if I call a.show and A is a type A, even though we're referencing an entire instance of C, A, in this particular case, it would look like A's method would fire. But A's method is virtual, and it has been overridden in B, and then it has been overridden again in C. So we simply continue to walk through the hierarchy until we find the most derived version of that method. Okay? Now this gets very interesting because this doesn't mean that we're always going to run into a situation where we'll walk all the way down to the class type that we currently are, that the whole object is. We could have actually got cut off at B. But we'll look at that in just a second because I know this can become a little bit confusing. Logan, let's go ahead and jump over to Visual Studio and let's draw this out. Let's actually code it.
Okay. First thing I'll do is begin a new application, and we'll start with a new console application. Now we need our classes A, B, and C. So we'll start with Class A. And Class A is going to have a public virtual void show method. And this method simply writes out the fact that we're inside of the show for A. So this will be a console write line. And we'll do
A dash dash dash.
So A
and then
show.
Yeah. Perfect.
All right. So we need a class B and C now. So we got class B. Class B is going to extend A. And class B is going to contain an override for show. So this is going to be public override void show. And inside of here, no, we don't want to call base. We want to do our own functionality, which is console write line. And for this, I'm going to get lazy and copy our other write line. Paste it in, only we're changing this to say that this is inside of B's show method.
Okay.
And finally, we're going to subclass this again into C, and to save time, I'm going to copy the entire class B, jump down a line, paste it in, except we're changing this to class C, and class C extends class B. And inside of its override of show, we're showing that this is C's show override.
Okay, good. So now we have our hierarchical chain in place, with C extending B, which was extending A. Okay? So now let's go ahead and jump back up to main, and let's go ahead and create an A.
So a variable of type A, we're going to call it A, and we'll store a new C object inside of it. All right?
Okay. Now let's go ahead and just turn around and call show from A.
So A.show. And then I guess just a console read line. So
yeah, just a console read line.
Console, grab our read line, and I believe that's
Don't execute yet, just build. And build is successful. So here, I want you to keep this in mind. So what we're doing here is we are creating type A. That's our variable is holding type A. But the reference it's pointing to is the object C. Okay, that's the object that was created. And C is a B and it's an A. Okay, just because of the hierarchy. Just as we go back towards those, as it becomes a B, we lose the scope of what was added in A. We lose that. We go back to A, then we lose that. But virtual, well, it has a very specific and special functionality here. And that's what we're going to actually see. So even though we're in A, and we say A.show, this is what happens. We really do hit A.show, but we don't execute it. Because the CLR says, ooh, it's virtual. That means that it may have a different implementation. It may have changed. So let's go to who derives this on our way to C. Okay? So on our way to C, we have to pass through B. While passing through B, well, it's an override, so it has a new implementation, but that means that going to C, it may have been overridden again. So we're now going to drop down. So we still have not fired a method yet, or executed a method. So now we come down to here. This is the last one in the chain, and we say, yeah, indeed, it is override. So it continues this chain. Since it continues the chain, this is the one we're going to fire. C show. Okay. So go ahead and run it, Logan. Let's make sure that's what it says. Look at that.
C show.
C show. So go ahead and close that. Now, to prove my point about we're going to walk down the hierarchy until we reached the most derived version of it for that object. That's the key thing. Because even though we can go all the way down to C, what if the object was not of type C? The object that was created was type B. That means we didn't extend all the way down that far. That means that particular implementation did not happen. So the most derived version would be B. So if Logan was to come back up, and instead of saying a new C, he creates a new B, and then once again he runs it. So right here when we run in A.show says, okay, it's virtual, so let's walk to the next class in the hierarchy, which is B. And in this particular case, it's overridden, so it is continuing on, okay, with the same method. And so he's overridden it with a new implementation. But B is our final, it's our stopping point. Because this is the object we've created is of type B, which means we're going to see B show. Let's go ahead and run it.
And there's our B show.
B show. There's no reason to walk down to C. It wouldn't make sense. We didn't create a C. That's
right.
what you got to understand.
It simply wouldn't make sense to go to C because C's implementation might have to do with the state of C. We don't know about the state of C if we are of type B, so that would be completely irrelevant to us.
That's right.
So we walk down to the most derived method most derived method on the way to the type that the class actually is.
Exactly.
We stop once we reach that class, even if C, and in this case C does override it again, but it's irrelevant to us. We actually made it all the way to B, and that's the one we were looking for.
You got it. Now, remember, as we're walking down the hierarchy, getting towards the most derived version of the method, we could run into a roadblock. We really could. Class C could implement a brand spanking new version of show. We could do a new virtual right there. So if we do a new virtual, it becomes a brand new one, and which can be overridden by anybody that extends C. Let's do that. Check this out. This is where things are going to get really interesting. What I'm going to do back over here is I want to actually put a roadblock right here. Even though we have an instance of C.
So we'll have to set that back to C.
You'll have to set that back to C. I want us to check here, and then walk down to here, and hit that roadblock and be forced to fire Bs, because we can't go to C. So let's jump back over to code. To do this, it's real simple. Several ways we can do it, but first of all, let's go ahead and set up top to C.
All right, so we're going back to a C for our actual object.
So the object is going to be the final class in the chain.
We could run real quick just to show. There we go again with our C show.
Very good idea. All right, now let's jump all the way down to class C. And at class C, what I want to do is hide the original show that we've been inheriting and overriding. I want to hide him with a fresh, brand new virtual show that can then be inherited and overwritten by any further extensions to Class C. So, Logan, go ahead and take out the word override and replace that with new virtual.
So public new virtual.
Okay.
Or new public virtual, or however you have it.
Yeah, like I said a few minutes ago, however you want to arrange it. In this particular case, we're just going to leave public outside. So this is a new virtual show method. New, ladies and gentlemen, what does new do? It hides any inherited members with the same name. We have just hid this show method that has been slowly being inherited down the chain and overridden each time. We've now created a completely new one in C. So check it out. This really does drive home the point of what I was saying. We create a type A. Since it is of type A, we start out by first pointing to A. And that's where we start walking from. We don't start at C. We start at the type we are representing at the moment. And what type are we representing? We're representing a type A. So we start at A and we go, oh, it's virtual, sweet. Let's walk down. So over here, let's go in our object type. So we walk down. Actually, I'll do it out here. So here's our new one. We walk down to B. All right. So B is definitely more derived. Well, let's take a look at C. So the CLR takes a look at C, but says, oh, no. C is a whole new thing. So since it is a whole new show method, we're not going to have any part in that. So who offered the most derived version of show? B did. We started at A, and we continued walking down the chain as long as we stuck with that same show method until we reached the most derived point. So what we should see when Logan runs it now, because C contains a, in fact, I'll just jot it down over here. Oh, erasers. So much fun today. What we should see, since once again we have a new virtual, is B show. Because this creates a roadblock for us. So who contains the most derived version of show? The last person to do the override. Him.
So that would be B.
That would be B. Let's run back over to Visual Studio.
And all right.
And is everything set up? I believe so. Let's go ahead and run it.
And look at that. B show.
B show. This is very, very important to understand. Here's another really interesting one. This is going to be cool. Go ahead and close that. What if let's jump down to C and change C back.
All right, so this is jumping down to C.
Back to an override.
All right, so this is public override.
So now we know with the type A that if we were to call upon A's show, since it's virtual, we'll walk our way all the way down the hierarchy to the type that we actually are, the instance, which is a C, and we'll execute that particular method. What if in B we want to have our own show that's private to B, for heavens knows whatever reason? So we're going to force hide show inside of B. But that doesn't mean it's hidden in C. C picks it right back up and keeps running. So Logan, let's take class B and change that to a private. All right, so we'll go ahead and do a private void show. All right, so now with a private void show here, let's go ahead and take a look at what happens. Now, are we going to be able to get all the way down to C? That's the question. Who's got the most derived version? We are of type C in the end, after all, aren't we?
There we go. We're making a new C object.
So we must wonder. Let's go ahead and run it. Check it out.
So we did indeed make it all the way down the chain to C.
We just simply skipped. B does not contain a derived version of it. C didn't lock us up whatsoever because C continues with the, that's the point I'm trying to make. It continues with the original method that we started the call on.
Because see, what's happened here in B is we made show private. That takes show out of the mix. As a matter of fact, I forgot to put new. So we were actually getting a warning. So if I made this a new private void show, so we were getting the warning at the fact that this was hiding show, but here's the key. It was private. It was only hiding it for B, because it's private, to B. C has no knowledge of B's show method.
Nope.
No one has any knowledge of show's method except for B. And in that way, it kind of just stepped out of the game as far as this virtual method show was concerned. Which means as far as this chain jumping was concerned, we look at this and see that it's virtual. We jump down to B. We say, does B override show? It does not. This doesn't count. It's inside of B only. All right, well, he doesn't count. Let's jump to C. Okay, C overrides, C gets shown. This is much the same as though we had commented out show altogether in B. So now it's like we have a gap in the chain.
Right.
We start at A, we jump down to B, B doesn't do anything with show. We jump down to C, and we can see that if we run, we again get C's show.
That's right. Very cool. Is there any more demos you want to do with this particular example? Just while we're here, having a good time.
Nothing example-wise comes to mind. Just to point out that this is the basis for a very convenient control system when we get back into the world of game design.
Heck yeah, it's convenient. We're about to put it to use in just a second. We're going to go back to that printer example and create a Word application and everything. Yeah.
But yeah, this is the
Logan's looking at me like I've lost my mind. That was great.
But this is really the basis where you can have a control system that works on the base type.
Mm-hmm.
Then you can place derived things into this base reference, be it a variable or a list.
Okay.
But then as you call functionality on this base, you can have whatever extended functionality actually have occur without actually having to cast anything yourself.
Right.
You never have to worry about the final types. You never have to worry about the derived types. You can just call methods for base types, but then due to the nature of virtual, they will actually go through, look all the way down the chain to the most, I guess you could call it most relevant defined type. Most relevant defined type that's actually of the type that you need, and execute that one instead. So that way, you could place an enemy into a game item list, tell the game item to update, but the enemy's update code is what actually gets run.
That's right. And Logan, let's put all of this to use. If we all think back for just a minute, okay? Come back in here and find which one of these. So not that one. Not that one. Ah, this one looks good. So let me go ahead and hide my tools for a second. Here's what I want to do. Just for some good fun. I want to actually code this. I want to code a base class. Then I want to extend that base class. I want to create a representation of an application. And guys, we're just doing this on the fly, so everybody just kick back and grab your coffee or soda and enjoy. I want to create this application, and I want the application to have print behavior in it. And with print, I want to be able to, something along the lines of, it's going to have print. But we saw before when we gave them that little example of coding the little printer thing, what did we do? We actually created an instance of the actual final derived type. In other words, a laser printer or an inkjet, yeah, whatever. But in this case, I want to work in the exact same way we've been demonstrating the ability to cast to something that's very high level, but have its behavior of the very specific low-level class get executed. So I want to be able to say, printer, take in a printer, or print, take in a printer, that we would just call printer. And let's take in some data. Okay? So this way, we don't have to instantiate. We will be instantiating a specific printer, but let's just store it in a generic printer, because each of the specific printers in the end are, well, they are just printers. So let's put this together. Let's just have some fun with it. We're just going to make this up on the fly. So go back over. I'll walk you through what I got in mind. First, let's start out by just discarding this application, starting a new one.
Thanks, you said I didn't keep the other one because it sounds like we're going to have.
I'm sorry. It just with you kind of wrapping everything up.
In the end, it's probably better this way because we get to start from a clean slate. So, like, well, what came from the old example? What goes in the new example?
Because this is, you were saying you were kind of wrapping everything up nicely with a bow on it, and I thought, it'd be cool if we went back to our printer example and demonstrated exactly what you're saying, because it really is a very convenient and powerful feature that we have in front of us. So let's put it to use. So here's what I want to do. Let's start out by making a class called printer.
Okay. Begin with the base printer.
And inside a printer, let's go ahead and just create a very simple virtual print method.
We'll make it public as well, so we can get to it from outside. So,
okay.
Or did you want it something other than public?
Yeah, public's fine. We're right now we're not worrying about access modifiers and all, except
so public virtual void
simple
print.
Okay.
And print should probably just take in a string for data.
Yeah.
So this isn't really anything different than we've done from the last example so far.
Nope.
Simple stuff.
And inside there, go and just do a console write line and say warm up if necessary and print. Exact same thing.
So warm up. Oh yeah, if necessary.
And then let's go ahead and write out load paper.
So we've got load paper. All right.
Okay. Now let's go ahead and extend the printer class into a laser printer.
Okay. So we have a laser printer. I'm confused with words there for a second. This is going to extend printer. And inside of it, we're going to override print. So this will be public override void print.
Boom.
And let's see, with the laser printer, we do want some of the base functionality, so we'll call base.print.
Be careful with what Logan said. Not some of the base functionality.
Well, yeah, I was saying.
We want the base functionality.
Yeah, extra words you need to remember. But yeah, that's what that means. We're making a call to base because we want...
Well, because we need to warm up if necessary and load some paper.
Exactly.
All right, so now let's go ahead and just say...
so we'll do a console write line for laser print.
Laser print, yeah.
So this is a laser print. And then you want a blank line and then some data.
Yeah, sounds good.
So blank line and then finally
print out our data.
So our last write line will be to print out the given data.
Beautiful.
And
now let's go ahead and just copy that entire class and paste it and change it over to an inkjet printer.
All right, so this new printer will be an inkjet printer. And then when we begin printing, we'll indicate that this is going to be an inkjet print.
All right.
And we're also calling upon the base functionality and then writing out the data.
Yep, very good. So now go back up a little bit and put all that in a region called printers.
So region for printers. And then we'll jump to the very end and we'll end off that region.
Nice. Now go ahead and collapse it for me.
All right, so before I collapse it, let me do a build, make sure I don't have any syntax errors. All right, now we're good. So there we have our printers region.
Excellent. All right, so now go right above printers and enter once or twice. All right, now create a new class called application. And we get away with this because this is just a console application. If it was Windows, we might
have a conflict, but
run into some interesting possibilities. So inside here, let's go ahead and create and this here is us not needing to create a virtual method. Let's just go ahead and create a regular method, a public method called print.
Okay. So we'll have a public void print method.
Okay, and it's going to take in a printer.
All right, so this will have to be of type, there we go, printer. Call it printer.
And then take in some data.
So we can take in data in the form of a string.
Okay, very good. And then inside here, all we want to do is call on the printer's print functionality.
So we can take the reference to the printer passed in through the parameter. So we can say printer.print and feed it data.
All right, awesome. Now check this out. Let's go up and create our word processor now.
Okay, so you want to, let's
so
make
application space word processor.
All right, application word processor.
Equals new application. All right, now let's go ahead and create a printer real quick.
Okay, what kind of printer do you want?
Well, let's begin by just creating a generic printer. So printer printer.
So printer
equals new. I don't know. Let's give it a laser printer.
Sounds good.
Very nice. Now let's just call upon our word processor to print out a test page. Watch how easy this is, guys.
So word processor, excuse me, dot print.
Now, all we need to do, look at this. It's looking for a printer, so let's send it our printer. And now let's send it some text, test page.
So here we go with the standard test page from before.
All right, make the T capital.
Yep.
All right.
I'm on it.
All right, and then a console read line.
Console read line. All right.
All right. Check this out. Notice up here, we're just dealing with, it's like, it's generic in a sense, in the fact that we're just dealing with a printer. We're not dealing with a specific printer. We're dealing with a printer. So when we tell our word processor to print, we just tell it, here's our printer. Now watch this. Run it. Warm up if necessary. Load paper. Laser print. And then there's our test page. So we just had a laser printer do its thing. Close that and change laser printer over to a...
maybe to an inkjet.
Into an inkjet.
All right. So
that's all he changed is just that. Let's run it again. Ladies and gentlemen, look what we have. Warm up if necessary. Load the paper and inkjet print. Ta-da. Now, we have taken the example that I rattled off at the very beginning about a real-world scenario where we have printers, and they're polymorphic in the sense that they all print, but they all take it upon themselves to handle how they print. So it's all different, though in the end it's the same thing we're looking for, okay, the same end result, if you will. And we have just coded that entire scenario, but we've used the nature of virtual method execution and hierarchies to our advantage here. And this is so, so important, because all we're doing is slinging around a printer. When you talk to your friends and all, and you're like, "Hey, print this," you're just, it's common, you know. You just sling out print, you know. You're not specifying which one. This guy knows what object he's pointing to, and we're using that whole. We execute the most derived method if it is virtual that we call upon. Well, when we called upon printer to print, we're basically taking a look at in print right here. So when we call upon it to print, let's go down here. What type are we when we come into here? Well, printer is pointing at, okay, printer being right here, he's pointing at just the high-level class. Now remember, the reference is to the whole object, which is a laser printer, okay, or an inkjet, whatever it is at the moment. But we're pointing at the type at the moment as a printer. So when we go to execute print in here, we see it's virtual. So what do? We walk down the hierarchy and check the next guy. Are you more derived of the same print method? And check it out. Let's say we have a laser printer. Yes, it's overridden. This is and there's no keyword new in there. This is a more derived version of print. And this is where we end because we're a laser printer. So this is what we execute. Now the very first thing we do, of course, is call the basis print because we want the common behavior to take place. So the common behavior executes, and then we return back and we do the specialized behavior for this particular object. Okay? And because of that, we're able to just simply deal with a printer. Anything you want to add, Logan?
And from here on out, we don't have to worry about who writes or extends printer. We can always use it in the same manner. That means someone else could write an entirely different CS file you could import, and they could write an entirely different assembly. And if that assembly was utilizing or knew about printer and application, any future printer could be written for the system.
That's right.
So, as a matter of fact, if you don't mind, we could, of course, make another printer in the same file. What I'd like to do is add a file to this project. Add a new item.
Because Company X made our holographic printer
So
for
let's say
us.
we're Company X now, or Company Y. We're making work. Someone outside the scenario, we're making a new printer for this print engine and application system. So let's make a new class called holographic printer. And a completely different file. Though because the namespace is the same, this is more or less essentially the same thing as writing it in. It just makes it look a little more external. But here we've got our holographic printer, and since we're in the same namespace and have the same references back to the main program, we could extend printer. And inside of holographic printer, we could do a public override void for print. And for the holographic printer, we'll keep with the same mentality. We're not going to call upon base because we're significantly changing the way this works. We're not using paper anymore. Instead, we're just doing something like, let's do the same laser calibration thing. So we could do a console write line. And we could write out calibrating laser. And then, let's see. Then we write out holographic print. Holographic. And then a new line. So let's write a blank line out. And then finally we could write out our actual data. So we do a write line for data. And then we have written a new holographic printer. If we build, everything builds just fine. Now, if we're somewhere in the print engine, and we'll call this the engine section where we have our application, we can have our application print out by using a holographic printer. So that's all we changed. Now we said that, all right, we're using a holographic printer. We could even be out in this file and make an entirely new application to go along with the holographic printer, but the idea is that we're using this application print engine. So there we go. The only thing we've changed in the main source file is that it's now using a holographic printer.
Okay.
If we run, everything runs just fine, only now we're doing calibrating laser and holographic print. And then we get our test page.
Very, very nice. Yeah, I'm glad you put that in another file, because one of the things we will generally do when our code's a bit larger than what we've been doing with these little snippet examples is create different class files. So the laser printer would have been its own file, the bubble or the inkjet would have been its own file.
So it's almost like you could say we've gotten this application project from someone else. We've extended it by writing a holographic printer, but we did not have to change anything in application. Application stayed exactly the same because we were handling printer in a generic manner, in a base manner.
That's right.
So we were just calling upon print. So it was up to us to make sure that we properly implement a print method, but what we do inside of it is up to us. So the functionality can be defined by whoever wants to extend this program now.
Exactly. Ladies and gentlemen, this is extremely important to grasp this concept because we're going to begin using it a lot, okay? It may seem a little overwhelming or confusing at first. If you feel that way, I would recommend taking a small break and then coming back once you feel a little rested and watch this video again. It is very important that you have an understanding of what virtual methods are and what benefits you get from them. The ability to override their implementation with new implementations in derived classes. That's so important. And it's very important to understand override as well, that you can only override, virtual methods. So that's very important. Now, of course, there's other things that can be virtual. We have virtual properties and etc. But I don't want to get into those right now. We'll start dealing with those as they sneak up. But of course, we can have virtual members. That's the point to understand here. Our primary focus has been on methods. But you need to understand those things, and then you really need a clear understanding of when you have an instantiation of an object, but the type variable is not pointing to your final instantiation type, such as enemy, but instead is pointing to something else in the hierarchy. So I have a game item, and instead of it pointing to enemy, it's just pointing to game item, so I can treat it in a generic sense the exact same way we were treating printer in a generic sense. It's very important to understand that when I say game item, let's say the game item's item.update, that what's going to happen is if the method happens to be virtual, the CLR is going to start walking through our classes looking for the most derived version of update. which means we could very well walk all the way down to the enemy, and then we'd run the enemy's update. That is very powerful. Okay. Now you can run into scenarios where through your own coding you could block that from happening if a class between game item and enemy creates a new version of that particular method, like a new virtual. Okay. That would cause it to stop and cause the game items update to run, because we can't execute the new one because the type that we are looking at is a game item. So we have to start there and stay with that update. Okay? Is that pretty clear, Logan?
Right. You're setting up a scenario where you always get a chain jumping effect, so you get down to the most derived relevant class, but just keep in mind that that's not an absolute. You can go in there and mess with it and basically break that chain, put a blocking point in by redefining a new virtual method or even just a new method at that level.
That's right. And so that means it won't run that one. It'll run the one right before it. Okay, so let's go ahead and jump back over to the whiteboard. Those are the most important things that you need to understand out of this video. So let's go ahead and jump back over here and scroll back up. So that is the nature of virtual methods in the hierarchy. So finally, we've got rules of virtual and override methods. I'm just going to throw a few very common ones. Actually, this will be most of them at you. So let's go ahead and come up here and just jot down rules. And let's start out with virtual methods. So virtual method rules. Now we've got 3 of them that we're going to look at. First of all, this isn't rules. We're just all relaxed right now. Just very common, natural conversation we're having. Yeah, there we go. I'm putting a bunch of weird words out there. All right, first of all, every single method inside of C# is rather virtual or non-virtual. There's no other kind it can be. It's rather virtual or non-virtual. So some methods are like an override method. It's like, oh, it's an override method. It's not virtual or non-virtual. Actually, it's virtual. It's implicitly virtual, which we'll talk about in just a second.
And we've seen that.
We actually saw that because we were able with A, B, and C to continue overriding it. But every single method is virtual or non-virtual. And with that being understood, then you can understand that non-virtual methods cannot be overridden. Okay? Obviously. So you have to have the virtual keyword in there. Alright. Next, you cannot use virtual. So you cannot use virtual with, and this makes so much sense if you just stop for 2 seconds and think about it. You cannot use virtual with static, abstract, or override modifiers. And think about it. Static means there's only one of that class. It cannot be instantiated. So how would you have a method that you could override in another class? Okay? Abstract. Abstract requires for you to go in there and override it. So it is virtual by
nature of it being abstract.
By nature of implicit. It's implicit. Bleh. And then finally, override is also implicit virtual. Okay, so you can't add those into it as well. So you can't use those modifiers along with the virtual modifier. Okay, and the third one we're going to take a look at is a virtual method cannot be private. So I'll just put cannot be private.
Because there would be nothing you could do with it. There would be no reason for it to be virtual.
You can't see it from outside the class. So if you have a derived class, a class that inherits from it, it can't see it. So how could it possibly override what it cannot see? So it cannot be private. Okay, that's very important. Now let's take a look at our override methods. And there's several of these. Our override method rules. First of all, the override method must have the same signature as the virtual method that's being overridden. So same signature. And I've already mentioned that several times as Logan was coding. Because otherwise, think about it. The moment you change up the signature but the name's different, now you're overloading. It's a different thing. Okay, so just think about that. The signatures have to match in order for you to override it. Because you're simply saying, take this method, and override its implementation. The moment the signature is different, it's an overloaded method. So it's a different method. So you can't do that. Okay, so same signature. Next. You can only override virtual, abstract, or you could say override methods. Okay, so you can only override virtual, abstract, and other override methods.
And really that goes back to what you were saying a minute ago, where you only have two kinds of methods, non-virtual and virtual.
That's right.
Virtual methods are ones that are marked with virtual, abstract, or override.
Right.
And so those are your virtual methods. Basically, override can only be used with virtual methods.
That's right. And of course, abstract, remember, that's implicitly virtual. And override is implicitly virtual. So that makes that's just common sense. It makes complete sense if you think about it. You cannot, so let me get this cannot in here. This is important. Just like the cannots up here. You cannot use overload.
Or override.
Or override, I'm sorry. With the following modifiers. So you cannot use it with new, static, virtual, or abstract. How could you possibly say this is an override virtual method? Yeah, that doesn't work.
It's almost the same thing as saying this is a virtual method that we're overriding.
Or the same thing as saying this is a public-private method.
Yeah, it's the same idea.
So you can't do that. Also, all right, you can. So if you can't, there's some cans. You can only use override with virtual, abstract. Wait a minute. I've already given you that one. Hang on. Let's scratch that all together.
That one was duplicated from before.
Yeah, that's what I get for copy and paste. Making sure I hit all of these notes for you. Pulling everything out of my mind is almost impossible when it's all jumbled up right now. Okay. Override methods are implicitly virtual. We mentioned that, but we didn't put it down as a rule. So they are implicitly virtual. And override methods must have the same access modifier as the overridden method. This is extremely important. I'll just put same access level. You can't have a virtual method public and then try to override it and set it to private. You can't even, you might say, okay, that's a big change. I can see why. You can't have it as public and then change the new one to internal. Even though they both act as public inside the class, that will still cause a problem.
Or you couldn't change it from public to protected.
Yep.
And just slightly change it, because protected would be perfectly valid otherwise for something that's inherited, because, I mean, you're inside of that hierarchy.
That's right.
But it would change the access modifier, it would change the access level, so that's not allowed.
So keep that in mind. The access level must be the same. Otherwise, the compiler will not be happy. All right, so that's the rules with virtual methods and override methods. Actually, almost every bit of it is just common sense. As long as you have a good understanding as to what static, abstract, new, what these different modifiers do, then there you go. As long as you have a clear picture in your mind as to what's going on, okay? It's all about inheritance and us inheriting a method that we want to redefine the implementation of. And that's all it is, okay? So with that, let's go ahead and jump back over real quick to our board, make sure everything is done. So we'll just turn this off, and we'll come back down here. And that takes care of the rules of virtual and override methods. All right, so this is going to bring us to the end. So we've talked about what polymorphism is. In the end, it's taken on many forms. And we have definitely seen that here through a class acting as different types. And we've seen it with behavior acting differently with different classes. Okay, so virtual and override methods, we saw that's how we create the ability of being able to go in there and change the implementation of a method in a more derived class. We took a look at syntax, basically just throw in the keyword virtual or the keyword override into there, but we also did out a bunch of examples. We talked about the nature of the virtual method and the hierarchy. And then finally we took a look at rules of virtual and override methods. Logan, is there anything else you want to add?
Nothing comes to mind. I think that wraps it all up.
Okay, well that is going to conclude this video. Thank you very much, guys.